Hello everyone, I am Mohammad Kamran from Indian Institute of Technology Indore. I am a PhD student and working with Dr. Shuman Majumdar. The topic of my talk is redshift space 21 cm bispectrum from the cosmic dawn and the impact of spin temperature fluctuations on it. The outline of my talk is following: redshift space bispectrum, about its magnitude and sign, impact of spin temperature fluctuations on the bispectrum, and finally I will discuss about the impact of the redshift space distortions on the bispectrum. The neutral hydrogen 21 cm signal from the cosmic dawn and epoch of reionization is expected to be highly non-Gaussian in nature, and this nature of the non-Gaussianity evolves with time. The two-point statistic like power spectrum would not be able to provide this non-Gaussian information of the signal. The bispectrum is one of the way to quantify the non-Gaussianity present in any field. And the bispectrum of the 21 cm field is defined by this equation, where B is our bispectrum estimator. So bispectrum is nothing but the Fourier transform of the 3-point correlation function in real space. So in this definition, our bispectrum estimator B will be non-zero if and only if the 3K involved in the definition form a closed triangle. Many people had been worked on the bispectrum of the 21 cm signal from the cosmic dawn and epoch of reionization based on analytical model and simulations of the signal. And these earlier works are based on real space 21 cm signal, as well as specified only for some specific K triangles like equilateral, squeezed and stretched K triangles. So for a comprehensive understanding of the non-Gaussianity, one should consider all possible K triangles in the Fourier space. However, in our work we have considered all possible unique K triangles in the Fourier space, and this plot represents all possible unique K triangles in the Fourier space, basically unique K triangles parameter space, where the horizontal axis represent the cosine of the angle theta, where theta is the angle between vector k1 and k2, and vertical axis is n is ratio k2 by k1. The conditions of unique K triangles is k1 greater than or equal to k2 greater than or equal to k3. This implies that n and cos theta will lies in the range 0.5 to 1, and this collectively implies that n cos theta will be greater than or equal to 0.5. However, the region with n cos theta greater than or equal to 0.5 can be termed as n cos theta space. In this plot, the top left corner represents the equilateral K triangles, where n is equal to 1 and cos theta is 0.5. The top right corner represents the squeezed K triangles, where n and cos theta both are equal to 1. And the bottom right corner represents the stretched K triangle, where n is equal to 0.5 and cos theta is equal to 1. The above half region represents acute angle triangles region, and below half region represents the obtuse angle triangles region. So this is the plot of simulated H1 21 cm brightness temperature map from the cosmic dawn, from very early to very late stages of the cosmic dawn. This is the map for our fiducial model, which is the mini quasar model with minimum halo mass 2 into 10 to the power 9 m-sun. And this is the output of the 1D radiative transfer grizzly simulation developed by Ghale et al. 2015 and 18. In our work, we have considered that the Lyman alpha coupling and X-ray heating of the IgM are proceeding parallelly. Now let me discuss about the different normalization of the bispectrum. The earlier work of the Watkinson et al. 2019 had been considered the reduced bispectrum. In this kind of normalization, the contribution of the power spectrum to the bispectrum normalized out, and also here this kind of normalization suppress the sign fluctuation of the bispectrum as well as amplitude fluctuation also. In our recent studies, we have considered a different kind of normalization of the bispectrum for the 21 cm field in the unit of millikelvin cube, and this kind of normalization shows the large sign and magnitude fluctuation of the bispectrum. Now let me discuss about the redshift space bispectra. So here we have plotted the bispectrum for all possible unique K triangles at 3 different K1 modes and at 5 different stages of the cosmic dawn. So as we move from left to right, K1 mode is increasing, and similarly as we go from top to bottom, Z is decreasing, redshift is decreasing. Horizontal axis is the cos theta value and vertical axis is basically the K2 by K1, which is N also. We can label the different stages of the cosmic dawn as very early stage, middle stage, late stage, and very late stages of the cosmic dawn, and similarly different K1 modes as small, intermediate, and large K1 modes. The blue portion of the color bar represent the positive values of the bispectrum, and the red portion of the color bar represent the negative values of the bispectrum. Now let me discuss about our findings. So here we see that at most of the time in the history of the cosmic dawn, from redshift 13.91 to 11.09, the bispectrum magnitude is largest as compared to very early and very late stages of the cosmic dawn. This is because of the large fluctuations in this regime compared to very early and very late stages. Next we see that around redshift 12.05, coupling and heating implies the largest fluctuation in the bispectrum, due to which we observe the maximum magnitude of the bispectrum. Coupling and heating produce the largest fluctuation in the signal, which implies the largest magnitude of the bispectrum. Now let me discuss about the bispectrum for the small K1 mode, and we see that around very early stage and for small K1 mode, in the entire n cos theta space the bispectrum is negative. However, as we move from very early to early stage for small K1 mode, then we observe a sign reversal of the bispectra. So this can be termed as first sign reversal of the bispectra, and topologically we can see that this is happening when the slope of the delta TB versus Z curve shows a sharp change in the slope from negative towards 0. And next sign reversal of the bispectrum has been observed as we move from early to middle stage of the cosmic dawn. This is happening because coupling and heating implies the largest fluctuation, and this implies the largest impact of the bispectrum, due to which there is a sign reversal from redshift 13.91 to 12.05. To see the continuous evolution of the bispectrum with redshift, we have plotted here the bispectrum versus redshift plot for the equilateral triangle at a small K1 mode. So here we can see that as our global signal transits from redshift 15.60 to 13.91, then the bispectrum transits from negative to positive. And second sign reversal has been observed when the global signal transits 13.91 to 12.05. So bispectrum sign again reverse. This is because heating tries to decrease the bispectrum magnitude, and heating along with coupling sharply decrease the bispectrum magnitude, and it pulls down it to negative. Next we see that when our global signal transits from 12.05 to 9.03, then since here only heating is dominant, that's why here the bispectrum magnitude is decreasing, not sign is changing. Next we observe that the bispectrum is negative in the vicinity of squeezed K triangles irrespective of K1 modes until we reaches ZS. So we define the ZS is the redshift above which the TS fluctuation dominates over matter density and neutral fraction fluctuations, and below which scenario is reversed. Next, we observe that for large K1 triangles in the entire n cos theta space, the bispectrum is negative until we reach a ZS value. However, across ZS, there is a sign reversal of the bispectrum. This is because at this stage, the negative sign of bispectrum is due to the TS fluctuation dominates over matter density and neutral fraction fluctuation. And here the bispectrum is positive because matter density fluctuation dominates over others two field. Now let me discuss about the impact of the spin temperature fluctuations on the bispectrum. So for this we have plotted here the quantity whole magnitude of B low Ts minus magnitude of B high Ts divided by magnitude of B high Ts. So B low Ts is the bispectrum when we include the spin temperature fluctuations in our signal, and B high Ts is the bispectrum when we exclude the spin temperature fluctuation, means when Ts is much larger than the CMB temperature scenario. So here we see that for small K1 triangles, the impact of the spin temperature fluctuations on the bispectrum is largest. Next we see that as we move from redshift 13.91 to 12.05 here to here, then the impact of TS fluctuation is increasing. Okay, so that's why we have observed the sign reversal of the bispectrum as you move from early to middle stage of the cosmic dawn for small K1 triangles. Next we see that for large K1 mode, in the entire duration of the cosmic dawn, the impact of the spin temperature fluctuation on the bispectrum is smallest and almost negligible around very early and very late stages of the cosmic dawn. So here we see that at redshift when Z greater than Zs, so there is the impact of the spin temperature fluctuation on the bispectrum is large, but when Z is less than Zs, for large K1 triangle, the impact of the impact of the spin temperature fluctuation on the bispectrum is small. So that's why here the bispectrum is negative and here the bispectrum is positive. So here is the sign reversal of the bispectra between these two stages. So here the matter density fluctuation dominates, here the spin temperature fluctuation dominates. Next we discuss about the impact of the redshift space distortions, and for this we have plotted here the BS by BR, where BS is the bispectrum in redshift space and BR is the bispectrum in real space. So if BS by BR greater than 1, this implies that RSD enhancing the bispectrum magnitude. When BS by BR ranges 0 to 1, this implies the RSD suppressing the bispectrum magnitude. And if BS by BR is less than 0, then this implies the RSD is changing the bispectrum sign. So next we observe that around very early stage and for small K1 triangles, BS by BR is roughly 1. So that's why we can say that there is a smallest impact of the RSD on the bispectrum. But for later stages for small K1 triangles, early to very late stages, RSD suppressing the bispectrum magnitude by more than 20%. This is because the BS by BR ratio is less than 1 or 0.8. And around very late stages for small K1 triangles, the RSD enhancing the bispectrum magnitude by more than 50% because BS by BR ratio is greater than 1.5. And finally we observe that in the vicinity of a squeezed K triangle for a small K1 mode, there is a sign change of the bispectra due to impact of the RSD. Next we observe that for large K1 triangles, the impact of the RSD is largest, irrespective of the duration or irrespective of the stages of the cosmic dawn. Now we summarize our finding. I summarize my finding. The bispectra for all unique K triangles provide a comprehensive understanding of the non-Gaussianity in the cosmic dawn 21 centimeter signal. So if you talk about the bispectrum magnitude, so bispectrum magnitude for cosmic dawn will be greater than the bispectrum magnitude for EOR. So here basically EOR means the very late stages of the cosmic dawn. The largest impact of TS fluctuation implies the largest bispectrum magnitude. And the bispectrum sign, so we have observed the bispectrum sign reversal at 3 different points. First sign reversal has been observed for small K1 triangles when the slope of mean brightness temperature versus Z plot changes sharply from negative towards 0. Another sign change of the bispectrum for small K1 triangles has been observed when coupling and heating both produce largest fluctuation in the signal. And third sign reversal has been observed for the large K1 triangles when spin temperature fluctuations transits with respect to its domination over matter density and neutral fraction fluctuation. So around Zs. Impact of the RSD, finally we observe that the impact of RSD is significant, which is basically greater than 20% depending on the K modes and stages of the cosmic dawn. Thank you.